Yes.
Что вы будете? Мы не говорим. Olha, eu gostei. Quando eu suspeito, se eu não montar redutor zero, ele não pode ter redutor zero.
Che poi ci dà l'ispezione.
Eu coptei tutta lista.
Ciò che fa cortigia questa
Poi, acho que já me deu zero.
ho visto.
Fanno che picca. Fiz tipo dragon, da vedi un po' qualche.
A gente depois tem que nós não conseguimos isto que eu escolhi a ti, só que é porque depois não fiquei
Na te slide che
Bisogna capire se e depois ter dentro do chão.
Yes, I mean, taking pictures doesn't imply AI. The AI technology that is coming later on, the next layer is AI. All right, shall we go with the answers? What is the main purpose of a convolutional 2D layer in the CNN? Right. Scanning the image to extract local patterns, right? Local patterns mean neighbors and how the different pixels are related to each other. Max pooling increases the spatial resolution of an image. Decrease. We decrease, right? So it's dimensionality reduction. CNNs preserve spatial relationship between neighbor pixels better than standard full connected neural networks. True? True. What happens to the feature map size after applying 3x3 to a 2x28 by 28 image without padding? All right? Is that clear? Gerta just explained it very, very nicely. What is the role of the kernel filter in a convolution? There, right? Okay. Searches for specific visual patterns. This is an error there?
No, it was.
It was a common error. Yeah. A larger stripe generally produces a higher resolution feature map. False?
I have seen some around that they
What does the stride mean? Let's start from there.
Stride.
Right? Okay. So let's say we go to stride equal to 5. We are leaving 5 pixels behind, and they will never be taken into account. Right? Would that be higher resolution? So false, right? Okay. Am I clear? Everybody is clear on this? What is padding used in CNNs? Third, right? Third. Any questions? No? why do CNNs typically increase? That's actually from it's a practical way of seeing it, but that's not always true. Okay, that's not a rule. But traditionally, what we are doing is that we are increasing the number of filters, 32, 64, 128, as the spatial dimension decrease. Okay, is it clear? I mean, intuitively it's clear, right? Why is that? Because now intuitively you understand how you extract features and what the features mean at every stage in the layers, in the network. Okay, this is very interesting. Now go back to yesterday. A traditional neural network receives 256 by 256 input image. Okay? And then we know that the hidden layer, the next layer, contains 1,000 neurons. How many weights are required?
65 million.
65 million. Why is that? Because we say, in a traditional approach, we take 256 by 256 flattened. So we make a very long vector. And then we know that the next layer contains 1,000 neurons. That means that every pixel needs to be connected with 1,000 neurons in the next layer. So that means that every arrow that goes from the inputs to the hidden needs to be counted as a parameter. So just multiplying the numbers gives you like what, 65 million. Which statement best explains why CNNs provide translational invariance? Here. Let me read it because I haven't. Okay, first one. So it makes sense, right? And we have a set of filters, and each filter now reused across different spatial locations of the image, right? So we know that the filter can be applied multiple times at a particular neighborhood. Okay, I mean, slightly off by 1 pixel the max, or the median. Okay? So good? Good, very nice. Okay, now, we're gonna go to the coding, and we have plenty of time. So I let you also play with this, especially the first part, because the first part is what Ogerta explained. And I'm going to just set up here quickly. Why don't you set up as well? So get Google Colab, your local machine, whatever you like. Okay, and in this lab, what we are going to discover or explore is actually image classification, right? It's a very, very basic task in computer vision. Actually, it's the easiest task in computer vision right now. Having a set of images, and what we're trying to do is to predict class 1 versus class 2, or assign probability values to class 1 and assign probability values to class 2, and we make a decision based on the highest probability, right? Now, the data set that you're going to use is a real world data set. It's not a MNIST anymore, neither fashion MNIST. It's a real data set, again, for benchmark purposes, but it is a good one because, first of all, it's not a grayscale image anymore. It contains 3 channels, but you will see, from a coding perspective, that doesn't actually change much. The image contains cats, and the images contain cats and dogs, and your task will be to classify the 2 animals, okay, to their corresponding classes. So in this one, what we're going to do is we will load the image data set, resize, normalize the images, you know why already, build the CNN using TensorFlow, train the model, evaluate, visualize. Visualize, we're going to visualize the learning curves. Remember, overfitting is a danger. As we are increasing the number of parameters, the overfitting can be there. So we need to inspect for overfitting. Learning curves are a great tool to do so. Okay, functions of loss or accuracy as a function of equals. Okay. Now, the first part is just importing the data sets. And again, TensorFlow, we are using TensorFlow, Keras, the layers. I'm using two new libraries, I don't remember it. Oh no, I think yesterday as well. Matplotlib library and NumPy. So both, one is for plotting, having nice visualizations, and NumPy is the one that actually is responsible for the arrays. How to handle multi-dimensional arrays, how to multiply, how to do certain operations with arrays. Now, checking the GPU is one thing. Again, I'm using a very basic machine here, so mine doesn't have a GPU. I'm receiving an empty cell. Maybe you do have, that's great. It's going to speed up your operations or your execution time. Mine won't, okay? So, and that's why I'm receiving. So, this line of code can be written in multiple ways. Do not actually try to remember it because that will change next year. Okay. Now, the image data set that we are using contains the 0 and the 1s. Okay, and for purposes, I am using the. There is an image data set by the way, in TensorFlow. Okay, but forget about this. I want to make a realistic scenario here, and someone is giving you the data, which is online. I gave to you as a zip file, right? So your task will be to take the zip file, store it in your directory, and from there unzip it and open the file and see what is in there.
Should be on the directory Google Colab?
If you are using Google Colab, that means that you should add the directory. So Google Colab knows where to search for your file folder. All right? If not, if you're using your local machine, one thing you can do is take the zip file, locate it in the directory where this notebook is located, unzip it, have it there, and with this line of code, path library.path, you can actually get access to the main folder. Good?
Or you can specify the full path, let's say, if the
Exactly.
file itself is not in the same folder with the data, so you have to specify the full path.
Exactly. So you can actually identify the path through Jupyter Notebook with the OS library. Okay? Now, if you open the data set, I can open it here. Do I have it unzipped? No. Assuming that this is unzipped, it takes time. That's in the cloud right now, so that's why it probably takes time for me. No, it opened.
Usually this happens in practice, so we don't start to run code and so on. First of all, we have to explore and to understand what data we have, let's say. So that is the first step. So let's see the images that we have. You can explore a bit 2, 3, 4 images in order to get an understanding about the problem. You know it's a simple one. You have just to classify them to cats and dogs, which is a binary classification. But this is the first task. You need to know what data you have. And later on, you think about how to pre-process and move next to this neural network. Yeah.
So inside the folder, cats versus dogs, there is 3 different subfolders: train, validation, and test. Okay? And what the nice piece of this is that someone has already made the split for you. And actually, this is very good. Yes. But no, actually, the author of the book. I did it for the project, so you are good for the project as well. But this, the book did. And the nice part of this is that you do not even have to worry about your splits. Why is that? So assume now that you have a data set, right? And with all images, no training, no test, no validation. All the images are within a folder. Now, what you will probably do is that you will go home, you will sit down, you will open the folder, and then you're gonna use a test, train test split function from scikit-learn, and split the data set accordingly. Some portion of the data images will go to training, some portion will go to testing, some portion will go to validation. Yes? Okay. What the issue with this is, I mean, it's not a real issue, but practically what the issue is. You did that, assuming that someone else does the same thing somewhere else in the world. Okay? If we do not use the same seed together, okay, I'm going to use the train test split, and I'm going to extract a different set of images for training, testing, and validation. Still, they're going to be cats and dogs, but they're going to be different. Okay? Now, you come up with your favorite architecture, CNN, with that many neurons, with that many filters, and so on. I come up with my own. We both run, and I'm getting an accuracy of 97, and you are getting an accuracy of 99. Okay, and we are meeting in a room like this, and we both show those two numbers. Is this a good comparison? Who is the winner?
You can say about context, I think.
Okay, now, very good. So the answer is that no one. But assuming now that both of us have used exactly the same architecture, you are getting 98, I'm getting 97. Who is the winner? The winner, not the loser. 99 versus 97.
99, the highest.
That's also. We,
Oh, no.
we don't
Okay, no overfitting. So both people have no overfitting. One is getting 99, the other is getting 97.
we still can't say with just one trial because there's
No, many
trials.
trials.
Many trials.
Many trials. Okay.
So it's the same architecture, let's say.
Same
But
architecture,
something happened during
same
the-
data, but different split. Okay, and 99 versus 9. Okay, I made 95, right?
And in terms of pre-processing, the same?
Same pre-processing.
Because that might impact as well.
So the training conditions stay, yeah?
Training conditions are the same, training strategy is the same architecture. Yes, yes. Same number of training tests. No, same data for training and testing.
Yeah, but they have seen different images. So
Everything is the same. Everything is the same. The difference is that the sampling. So you have a pool of data, and I close my eyes and I pick 5 cats and 5 dogs. You close your eyes and pick 5 cats and 5 dogs. Okay? We both do the same architecture, the same training, everything the same. I'm getting 95, you're getting 99.
a random selection.
Exactly. The sampling is the issue here.
Yes,
Okay?
You do have the dog here.
Very good. So, very good. So you may get images that are not representative. That is very common in real world scenarios. Okay? And there is no way to inspect this manually. So we're talking about now like thousands, even millions of documents, sorry, not documents, images. Okay? And if I close my eyes and I cherry pick like 100 for now, I don't cherry pick, I pick 100 dog images, the probability that I may pick some problematic ones is high. Okay? That will affect my training. Even if I'm using the same architecture as you do, that will affect my training. Okay? And that will affect my testing performance eventually. So, it really matters if someone gives you something like this. and especially when you have to compare architectures or models with each other. So it's unfair if you just use all the data and run a model and someone else does the same. You need to have a very clean or clear split like this. So this one, everybody knows training is training, testing is testing, validation is whatever it is. So now you can safely go and start comparing architectures with each other and say mine is better, I have a better idea, now I'm going to implement traditional versus CNN and so on. Okay? The split is important. And the people who are actually sitting there, they are called data engineers. Okay? And they are spending a good amount of time doing this. And it's actually more important than the model itself, than the training itself. Okay? So just appreciate this effort and try to mimic this type of effort for your projects. Do not just blindly go and cherry pick, select, blah, blah, blah. Now, every data set is engineered in that way that you do not have to worry because it's engineered in that way. There are no problematic observations there, everything is nice, everything is balanced, okay? Imbalance is something that we're going to see in the project too, okay? So one class will have much more observations than the other. Would that affect the final output? Yes. If you train, you will see that the accuracy probably will be 99%. If you just don't know what is going on with your initial data, you will say, I got 99% accuracy. Go to your manager and show it. If they believe it, that's bad for the business. Okay? But if they don't believe it, that means that your manager knows what is going on, what needs imbalance in the data.
Cloud convert.
Good? Yes.
I'm not able to download the zip file.
Okay, that's now the second
Via
challenge.
via cloud.
So if you are not able to download the zip file, that's fine for now because we have everything in the output so you can see. If you go home, download it. It's gonna take. I use the 100 megabps home. It downloaded for like 5 minutes. Or
No, I mean it doesn't give me the option to download it.
Oh.
I don't know why.
I'll come and check, okay? Or Gerta will come and check. There is a little trick there from Google Colab. So, sorry, from the Google Cloud. Others were able to download it? Yes?
I'm uploading to Drive to. It's 3 minutes left from 20.
Oh, from 20? Wow. Okay. Does it make sense what I said about the train test validation? Yes. You have a question? I'm coming there to the game. Yes.
Kiedy nie chcę downloadować,
CNS will be investigation like this. Yeah, so we're going to pick all, you see that there's a train farm. From that, we're going to use the whole, whatever is in there for training. And we're going to use a CNN architecture to train the model, train CNN model. Be able to actually separate the dogs and the cats from train.
Temperatura. Oh, E3. Și pe cât au unii fie temperatură necondiționată.
Eu din dat de cu
All of it. Have to do.
Ada to do nu știu bine.
Okay, now I'm going to open just for fun. And say that again from the beginning.
So if you have a data set, that is listen to training, how do we determine that it has included in that?
That was my question. What's the criteria?
Yeah. So the criteria is actually the data engineering criteria that you should set up. So first of all,
It's the given function or
yeah, I mean I can show you for the project that I did, but there are given functions. You can
There are
do it.
given
It's
functions.
pretty straightforward. But the first indicator when you are okay. Good question. I'm gonna repeat it so everybody can hear this question. I'm working at a company and the manager is giving me the whole data set as a folder. And one thing that the manager will also give me is the labels. Okay, I'm not talking about unlabeled without labels because then we start from the beginning. But labels. Okay, so cats, dogs, one folder with labels. Now, the question is here: what is the criteria to actually make a good split? Make something like this: train, validation, test. Okay. I assume that the quality of the images is okay. I assume. Alright? That's a good assumption. But the first indicator from a machine learning perspective is to check how many observations are in class 1 and how many observations are in class 2. This is really important. This is even more important than having few problematic images. Having few images that there is no dog even, or there is not even a cat. The network can actually figure this out if there is absence of an animal within an image. But if you have 90% of your observations belonging to dog versus 10% of your observations belonging to cat, you will fail badly in training, even if you use the best architecture ever. Okay? Simply one. The majority will be dogs. So what's going to happen when you're going to test?
Will be generalized into.
Most likely, you will always predict something as a dog. Okay? And before I said that the accuracy will be 99%. Yes, because your testing will be all dogs, right? And the only instance that you're going to give a cat, it's going to fail. Good? So this is actually has a name. It's called classic imbalance. Is this the only imbalance that someone can have? No. Imbalances can be on anything. So first of all, when you are dealing with data, one very common imbalance that you may have is on the attributes itself. So remember that when you are working with tabular data, you have observations as rows and variables as the columns, right? And then you are saying, okay, I'm gonna select a couple of features from those columns for my training algorithm. But then you are leaving behind a couple more others. For example, fraud detection. Okay, one of the columns, one of the eventual variables could be gender, male versus female, and you do not take this column into account. This is a hidden attribute, we call it. Okay, you make a classification. You get accuracy 99%. So you are able to detect fraud. However, you are not able to detect fraud based on gender. Simply because there is an imbalance on the gender. If fraud happens from a man, which is most frequent, that means that you will be able to detect it from a man. But if we change the gender, the fraud will happen from a female, you won't be able to detect it. Okay? This is called bias. Okay? This bias, and especially neural networks, fits into the input and propagates badly and magnifies through the network. And a small bias in the input data can actually magnify and become a huge bias in the final output. Alright? So pay attention to any aspect of your data, even those little things, like male versus female. Who wrote it? In the project, we have articles that are articles written in the Albanian language, right? We have a couple of categories, a couple of labels. So there was a total of 20 plus labels. I just reduced it manually to 7 labels. So there is one sports, one politics, one something else, one football, and so on. the task will be to actually classify these articles into one of the 7 categories. If the article is about football, your algorithm should say that this is football. If it is politics, it should say that this is politics. Okay? Pretty straightforward task, like what we do here, but for text. However, the data contains a lot of useful information, and I can tell you what type of information this is. The title of the article, 1. 2, the author of the article, the name of the author, the date when the article was written, and the source that it was produced, it was published. Okay? So all of those attributes are not taken into account when I'm doing classification. Okay? And you can imagine now, your mind goes directly, naturally to this direction, that if the source is a not reasonable source, if it is like a trash type of source, website that talks about conspiracy theory all the time, right? Your algorithm can actually confuse on the classification. That is the bias. If your author is like a journalist who is very popular journalist in Albania and very valuable journalist, then you can trust actually the decision. But if the journalist is someone, you know, random, right, who is, I don't know, talking about conspiracies all the time and so on, then probably you won't be able to lie. And much more than this, okay? But you see the attributes, how important they are. Good? I think I should stop here because this is day 5.
But this is very important, the fact to explore the data and to understand the data, because when I'm talking students, but everyone that is working with neural networks, so they always focus on having in place a complex neural network with so many layers and so on, and they do not focus on the aspects of the importance of the data and how we process the data and so on. You can build a very complex neural networks, you can add many layers in between, hidden layers and so on, but if your data are highly unbalanced, and this happens in many domains such as health, so if you are predicting disease, so you get data from patients and you have 1 million of data, and 95% or even more of these records will belong to the majority class, we call it, which means normal patients. They don't have that specific disease that we are looking for, and we have only a very small percent of records that they belong to the minority class, the other class that we want to detect or to do this kind of classification. And you don't have that, if you train your models with the full data as it is, 95% belonging to the majority class and 5% or less belonging to the minority class, the model itself of the network doesn't have enough instances or records from the minority class in order to learn, let's say. And this is very important, the process of having unbalanced data set in different domains, like in health that I'm talking, or in fraud detections, let's say. So they are highly unbalanced data set, and you have to tackle this problem to identify, but also to see how you can deal with these unbalancing aspects. And there are different ways that you can deal. Some might be downsampling, so you remove some, but this is not the best one that we suggest. So you can remove records belonging to the majority class. But usually what we do, we use different advanced techniques in order to balance the data set. One of them, it might be the SMOTE one that we use in order to synthetically increase the number of records that belongs to the minority class. So we are going to have to include some synthetical records belonging to